Hello everyone, Mr. Lake here with another chemistry lecture video. This is a big one. It's actually going to be a pretty short video, but it is a big transition into talking about one of the main things that we're going to be doing in this class, which is stoichiometry, which is it's really just more dimensional analysis, but it's tying in everything that we know so far about reactions and balanced equations, and it's bringing that into the math that we've been doing with conversion factors and unit conversions and dimensional analysis and all that. Very, very exciting day, very exciting video. Are you excited? I'm excited. Let's go. So, going back to the concept of balanced equations, remember that a balanced chemical equation represents it represents a realistic reaction scenario. How many different pieces are going to react together to form a certain number of other pieces, right? So because it is accurate in terms of the proportion of different ingredients involved and products formed, it represents the ratios of each reactant to each product and vice versa. So for example, in the balanced equation, 2H2 plus O2 reacts to form 2H2O. What that really means is that two molecules of H2 react with one molecule of O2 to form two molecules of H2O, sorry. Now, it also means that if we're at the molar scale, 2 moles of H2 react with 1 mole of O2 to form 2 moles of H2O. So it is displaying a relationship both at the atomic level and at the molar level. Anytime that we pull one relationship from a balanced equation for two things, it could be two reactants, two products, or a reactant and a product. Anytime we pull a relationship between those two things, it's called a mole ratio. So for example, in this balanced equation, there are a bunch of mole ratios that we could come up with. In this particular reaction, if we wanted to know the relationship between hydrogen and oxygen, we know that for every 2 moles of H2, 1 mole of O2 reacts with it. We also know the opposite. For every 1 mole, not the opposite, but the inverse. We also know that for every 1 mole of O2, 2 moles of H2 react with it. Now, why am I writing these as fractions? Well, don't they look kind of similar? Sorry, familiar? They should look familiar because they are conversion factors, right? Just like molar mass in the last video was a conversion factor, just like Avogadro's number before that was a conversion factor, this is yet another conversion factor that we can use. And we can come up with the relationship for any two things in the reaction. So if we want to know the relationship between H2 and the product, H2O, we know that for every 2 moles of hydrogen that react, 2 moles of H2O are produced. Of course, we could simplify that to a 1-to-1 ratio, but I'm just using the coefficients from the balanced equation. We also know that for every 2 moles of water that was made, it took 2 moles of hydrogen to make it. And if we want to know the relationship between oxygen and the product, for every 1 mole of oxygen that is used in the reaction, you can make 2 moles of water, which makes sense. And for every 2 moles of water that's produced, 1 mole of oxygen was used. So we can pull these relationships, we can pull these mole ratios from a balanced equation and then use them mathematically as conversion factors. And I realize that I'm taking a few steps here. I'm making some jumps, but hopefully the concept of conversion factors makes sense. Hopefully the concept of balanced equations makes sense. And so therefore this is not too much of a jump forward. What this is useful for is it's really useful for predicting reactions. It's useful for setting up reactions and making sure that you have a reasonable ratio of reactants. And it's useful for figuring out what happened in a reaction. It is very, very useful math for kind of predicting and evaluating and planning for chemistry-based things. So for example, let's say that you had 7 moles of hydrogen, H2, and you want to know how many moles of oxygen you should react with that 7 moles of H2 so that it all reacts and makes H2O. Okay, so what we know in this calculation, because we are going to calculate this, is we know that we have 7 moles of H2, and we want to know, our goal is to know how many moles of O2 would react with it. So we're going to start with what we know, just like always. All right, we're going to set up a little conversion thing. We're going to write 7 moles of H2O. Now, since the unit in the thing that we're starting with is moles of H2O, I'm going to write this down here. And since what we want to know is moles of O2, I'm going to write that up here. Just like before, right? We put what we know in the upper left-hand corner. We take those units, we put them diagonally down to the right, and we put the units that we want to find out in the upper right. That's why I was so insistent that everyone practice and use this setup and this ritual, is because it's going to just continue to be useful in lots of different contexts. But if you don't kind of have it cemented in your brain, then every single time I show it to you, it's going to feel like you don't know what you're looking at. So here we go. This is what we need. We need a conversion factor from moles of H2O to moles of O2. Where are we going to get that? Well, what we just did on the last slide is we looked at all of those different conversion factors. So we need a conversion factor for oxygen and H2O. What's the ratio there? Well, it's 1 mole, because there's an implied 1 here, 1 mole of O2 for every 2 moles of H2O. So that's what I'm going to write. For every 1 mole of O2 that's used, 2 moles of H2O is produced. I totally messed this up, everybody. And I feel horrible. It's asking about moles of H, not moles of H2O. So ignore the O. We've got 7 moles of hydrogen. Turns out that the molar ratio is the same, right? 7 moles of hydrogen. 1 mole of oxygen reacts with each 2 moles of hydrogen. So that means that 7 moles of hydrogen is going to react with 3.5 moles of oxygen. So how many moles of oxygen would react with 7 moles of hydrogen? 3.5. Now, how many moles of H2O would be formed from 7 moles of H2? I'm going to pause, disappear for a second, and give you an opportunity to solve this on your own. Plus, press play when you're done. I'm back. Let's solve it together. We want to know moles of H2O. That's our goal. What we do know is that we have 7 moles of H2. So we are going to set up a conversion. We're going to write what we know, which is 7 moles of H2 in the upper left-hand corner. We want to know how many moles of H2O that would react to form. We want to get rid of our units of H2. So we need a molar ratio from the balanced equation that tells us what the ratio is of hydrogen to H2O. Well, there's a 2 in front of hydrogen and a 2 in front of H2O, which means that for every 2 moles of H2 that reacts, 2 moles of H2O will be produced. That's our molar ratio. So mathematically, how we're going to solve this is we're going to take 7 times 2 divided by 2, which is going to be 7. And units-wise, moles of H2 is eliminated, and we're left with moles of H2O. So our answer is 7 moles of H2O. How many moles of H2O would be formed from 7 moles of H2? 7. That's the answer. So I hope that makes sense. This is a very small introduction to the way that we're going to use this. Really, mole ratios are extremely simple. They are maybe the easiest conversion factors to just grab and use. What makes them complex is when we start combining them with the other conversion factors. But that's a topic for another time. So that's it for today. Thank you for watching, and until next time, take care of yourselves.